Hello guys, welcome to the first lecture in series of lectures of magnetism. We'll try to understand the concepts of magnetism and we'll delve deep into every important concepts related to magnetism, magnetic effect and all the possible laws, and then we'll solve J advanced questions. So let's begin. So first we are trying to get into the deep philosophy behind magnetism. So there are two ways to define magnetism. One way is the classical ways of Michael Faraday, and the other way that was lately discovered after discovery of special theory of relativity and general theory of relativity of Einstein. So we'll try to understand magnetism with the help of with respect in the reference of relativity. Okay, so let's get started. So in order to understand magnetism in the reference of relativity, we have to keep this statement in our mind, and we have to assume that this statement is true, which is of course true, but at our standard of of, of, of academics, this statement means nothing to us, but it is true, it is trivial, and it holds true in physics. So we have to remember this, and by this statement we will prove that how magnetism is actually an influence of electric field. Magnetism is nothing but electric field into special accounts. So electric field and magnetic field are nothing but influence of charges, and magnetism is actually electric field. Magnetic field is nothing but an electric field from a different perspective. Okay, that's what you will understand. So special relativity says, or rather say general relativity says, that an object moving faster relative to other, for example, if let's say there are two objects A and B, let's say this is moving with velocity v and this is at rest, and this is, let's say, moving with velocity v1 and this is v2. So if v2 is greater than v1, okay, then we'll say that A is moving faster with respect to B, then object moving faster relative to other occupies less space. So if let's say this dimension is L, if A's dimension is L, then in respect with respect to B, this dimension will shorten. This will be something, this will reduce by some delta L. This will reduce by some delta L. Okay, and now this distance this length will be only L dash. Relativity says that time and length are not absolute, they are relative to different speed at different times. Okay, so that is what relativity says, and it says object moving faster relative to other occupies less space, and object moving slower. And if we say that this is first case, and let's take another case. If v2 is less than v1, then if this is dimension of v2, that is, let's say, L, then because v2 is then with respect to B, because A is moving slower, then this dimension will actually increase, because object moving slower occupies more space, so this will increase by some delta L on both ends, and now this distance will be some L dash that is greater than L, and this distance will be L dash that is less than L. Objects moving faster occupies less space, and object moving slower occupy more space. Okay, so that's the statement. Now let's talk about magnetism. Okay, now imagine that there is a wire. Okay, that is there is a wire in which electrons and protons and electrons are flowing. Okay, so if electrons and protons are flowing, if electrons are flowing and protons are at rest, because we know that protons are only electron flows in the conductor, and this is, let's say, this is a copper wire, then in any cross section we will have almost the same number of proton and same number of electron. Hence, if we assume any positive charge here, let's say any proton here, then there will be no impact. It will have no impact of these charges, because proton repels and electron attracts, so it will be at rest. Okay, so if this is if you assume a positive charge near a current carrying wire, it will be at rest, it will have no, it will experience no force at all. Okay, why? Because in any cross section, the number of electron and proton will be roughly same. Okay, now imagine another case. Imagine that this proton is actually moving with velocity. Let's imagine that this electron is moving with velocity v, and now imagine that this proton is also moving with velocity v in the same direction. If this proton is moving with the same velocity in the same direction as of electron, then in reference, then with respect to, I'm calling this b, then with respect to b, electrons are at rest. Okay, and protons are moving backwards. This is simple law of relative motion, backward with velocity v. So in respect of this proton, these electrons are at rest because both are moving in same direction with the same velocity. But but with respect to this proton, these protons are moving in opposite direction with the velocity v. Okay, now general relativity says that objects moving faster occupy less space. Now because with respect to this proton, now electrons are at rest, so they will occupy more space, so electrons will disperse out, there will be less density because they need more space, so उनमें दूरी बढ़ जाएगी because they need more space. And why they need more space? Because in respect to this proton, they are at rest, but this proton in the wire are actually moving, and objects moving relative to other occupy more less space, so protons will have less space here, so protons will come closer because they occupy less space. So in any region, with respect to this proton, in any region, number of proton would be greater than number of electron. Why? Simply because with respect to this proton, electrons are at rest, and general relativity says that object at rest occupy less space, occupy more space, therefore they will just scatter out. And relativity says that, and because proton is moving backward with respect to this, and because they are moving, so moving objects occupy less space, so protons will come closer, and in the reference of this particular proton, number of proton in the wire in any cross section is greater than number of electrons, and therefore this proton will be repelled. This proton B will be repelled. That's why we say that current that a moving charge, let's say Q, is if it is positive, is repelled if it is moving with velocity v. A moving charge near a current carrying wire is repelled if it is positive and attracted when it is negative, simply because, and we understood it with the help of relativity. So that's how it works. I think it's clear, and by this concept we can also imagine the force it will be experiencing, so we can understand that this is nothing but just an electric field, because there are more protons, so they will repel more, but there are less electrons to attract, so repulsion is superior, therefore this proton will be repelled. If it was electron, then protons would have attracted it, and electrons are not sufficient enough to repel it, therefore it will be attracted. Therefore we can understand that if from this illustration, if Q is electron and if it is proton, then in electron it is attracted and in proton it is repelled. And we can also imagine that the force that this proton would experience is proportional to charge and is proportional to velocity, because the more faster it will move, the more faster this proton will move relative uh, to this proton, and therefore they will condense more, and these electrons will scatter more. So this force depends on this q and v. Okay, that's how we can explain the existence and this performance of magnetic field in reference of electric field. So that's the first lecture. In the second lecture, in the next lecture, we shall talk about Biot-Savart law, and we'll solve JEE advanced compendium questions. So that's all for today. Thank you. Like, share and subscribe. Thank you.